Okay, so good evening, everyone. And before we start today's Asset Colloquium, on behalf of the Asset Forum, let me wish you, all of you and your families, very, very happy Diwali. And I hope this year would be a better year for all of us, and trying to, be able to interact much more physically and more meaningfully than we did in the last year and a half. And so with that, let me also take this pleasure of inviting on call today's speaker, Air Marshal Rajkumar. He's going to speak on a very nice topic. I think that is in some sense a context in which most of us keep talking about the Indian scenario, especially in the strategic areas and science and the technology developments. So the title is True Success Story of ATMANIRBHARATA, the Tejas project. So the project is going to be on Tejas. The talk is going to be on Tejas project, but also covering these new things that the country is heading to. And also I would like to invite Professor Vivek Datar on the call, who was actually instrumental in making this talk happen, and who will also formally introduce today's speaker. Before I kind of say what ASSET is for some of you who probably are not from TIFR family, I also want to welcome Clement Rajan, who is the elder brother of today's speaker, and younger brother of today's speaker, Philip Rajkumar. So ASSET colloquium, ASSET actually stands for Advances in Science, Engineering and Technology. I don't have to say the strong connection of ASSET with today's topic per se, but this is a forum at TIFR along with two other colloquia that happens on Wednesday and Thursday, respectively, for dealing with natural sciences and mathematics. So the ASSET colloquium deals with mostly on engineering and technology related aspects, and it kind of complements the topics that are discussed in the other two colloquia. These colloquia happen at 4 o'clock on Fridays. And of course, due to COVID, we have most of the talk these days happening on virtual platform like this. But I must also tell you, these days, if the speakers are from Mumbai and around, we also slowly started having it in the hybrid mode. So hopefully, at least if not end of this year, but early next year, we should start having a full-fledged physical ASSET colloquia to happen. So with those words, without taking more of the time of the speaker and also Professor Vivek Datar, now let me pass on the podium to Professor Vivek Datar, who will do the honors of introducing formally today's speaker. Professor Vivek Datar.
Thank you, Satya. It's an honor to be able to introduce or to provide a small introduction to Air Marshal Philip Rajkumar, who kindly agreed to give this talk. I should say that it was, I came to know of his association with Tejas through his younger brother, Clement Rajan, who happened to be my schoolmate from Bangalore. So I then, of course, saw some of his interviews that he has given on YouTube, and very impressive. So I wrote to his brother, and then he contacted Air Marshal Philip Rajkumar, and then he kindly agreed to give this talk. So I'll give a brief introduction. It probably just does a little bit of justice to his. He's done so many things that it's difficult to encapsulate them, but I will try my best to do so. So he's of course somebody who has got a large number of awards, the PVSM, the AVSM, VM, MID, and so on. I don't see the... this slide is not moving. Okay. So these are the awards, the Param Vishish Seva Medal, the Ati Vishish Seva Medal, and then the VM, and so on. So his early days were in Karnataka, born in Davangere, homeschooled in Mysore, and then he did his graduation in the Central College, which is a pretty old college in Bangalore. Then he went to the Air Force College and he was commissioned in 1962. He was associated with both Eastern and Western sectors for 9 years and served in frontline fighter squadrons. Then he went to the US to get training on gunnery. And then he was, of course, associated quite intimately with the September 1965 Indo-Pak War. And this is a picture of some of his colleagues. So this group was called the Tigers, and they were part of a squadron of the IAF. And so this is Philip Rajkumar here and some of his colleagues. And this is an artist's impression of a very daring raid that they did on Sargodha Airport, which is one of the chief airfields, I believe. And this is an artist's impression, of course. So this, I think, made him and his colleagues pretty well known. So this is a painting done by one of his colleagues. He received a mention in dispatches and so on. And then he switched to MiG aircraft, MiG-21, and then went to France for training to be a test pilot. And that was apparently a very rigorous training. And the course was entirely in French. So, of course, he would have had to learn the kind of French that was spoken there, because it's also different learning French in India and then actually listening to the French language. Anyway, he underwent that training, and then from then on, he became a test pilot. Some problem. Okay. His test flying career, he spent about 20 years in various types of fighter aircraft. These are the fighter aircraft that he flew on. And also, not just fighter aircraft, but also transport and trainer aircraft. So these are some of the pictures of the trainer aircraft that he flew on. He's probably one of the very few people who have flown all the top-notch fighter aircraft in the world. The Russian MiG-29, Mirage, and the Jaguar, the US F-16, and finally, of course, the Indian Tejas. So he was in charge of a squadron in the Punjab sector, the operational assignments, and then in the central sector, Jaguar base. Then he became associated with the so-called Aircraft and System Testing Establishment. This was established in Bangalore in 1970. First, he was a test pilot, then a chief test pilot, and then commandant. The Tejas came about through the intervention of Dr. Abdul Kalam, who was then the scientific advisor, and he asked for his deputation specifically to the ADA in Bangalore to plan and execute this program of Tejas. This, as has been said, was probably India's most ambitious and risky aeronautical development program, because there were many, many new technologies. So coming to the honors, of course, I already said that he had the Param Vishesh Seva Medal, the Ati Vishesh Seva, and the Vayu Sena Medal. Shown here, he was the president of the Aeronautical Society for 2 years and honorary fellow. And of course, he retired from service in 2002. I will not say very much about his use in Tejas because that is what is the topic of his talk. He has flown, of course, more than 5,000 hours in about more than 50 different types of aircraft. He's an avid reader, ardent trekker, and loves sport, still plays golf. And of course, he has apparently a very good sense of humor, which we will probably have the pleasure of listening to this talk. So let me see, somehow I can't get the next. Okay. So this is a picture taken in February 2020. He was in the cockpit of the Tejas trainer, probably one of the oldest persons who has sort of been in such an aircraft at the age of, I think, 79 or something. So with these few words, I now pass I hand over the stage to Air Marshal Philip Rajkumar, and we look forward to a very enriching talk. Thank you.
Yeah, thanks, Professor Datar. I was wondering if Mr. Clement Rajan want to add one or two words about his illustrations, brother.
Nothing more. Dr. Vivek Datar has described everything that I have had to say, but Rajkumar has been my inspiration, my role model in life. And I've tried to model being a good person like the way he is, with this sense of humor. So I'm greatly indebted, Raj, my leading light.
Thank you. Thank you very much for those words. I think now it's the time maybe to invite today's speaker. Sir, you can share your slides.
Yeah. I'll just close this window. I go to share slide. Okay, can everybody see the slides?
Yes.
Yes.
Yeah, it's in full screen.
So I'll start by thanking Vivek Datar for that very generous introduction, and my younger brother Rajan for all the nice things he said. Thank you all very much for inviting me to the Asset Colloquium, and I hope you all will find the talk interesting. So I will move on to the first slide. The slide is not moving. Why is that?
Can you?
Rajkumar, at the bottom left corner of your slide, you'll find the arrow. There's a small arrow. Click that arrow. Bottom left corner.
Bottom left corner.
Yes.
Yeah, okay.
That one. That'll click it, yeah.
Yeah, okay. This, I had the great good fortune of working under Dr. Abdul Kalam for 5 years from 1994 to 1999. His great saying was, you have to dream before your dreams come true. So unless everything starts as a thought in somebody's head. And Dr. Kalam was a great inspiration in my life. Now, here you have a photograph of the old MiG-21 biz aircraft and the new one. This is the old bringing in the new because the Tejas was meant to be a replacement for the MiG-21, which was going to go out of service starting from the mid-90s. But because the Tejas program got delayed, we had to do an upgrade on the MiG-Biz, and it is still 3 squadrons of that are flying, while the Tejas has just started entering service. Now, Tejas was, as said earlier, India's most ambitious aeronautical project, but also the most criticized. It had a barrage of criticism from both the print and electronic media and speakers, and even in Parliament. And fortunately, today it has become the country's most successful project with an outstanding safety record during development. Now, I'd like to focus your attention to the aircraft, the Tejas aircraft itself. The configuration, the external configuration chosen was a delta wing. The delta wing has please follow my arrow. It's got an inner wing sweep of 54 degrees and an outer wing sweep of 60 degrees. It's got trailing edge ailerons here, 2 ailerons here and 2 ailerons on the other side. You have a fin and rudder here, and then you have the engine, and over here is the brake parachute housing. The patchwork that you see on the wing this is a development aircraft, and being a composite wing, we had to create electrical pathways to conduct the static electricity and lightning discharges and all that. That's why it's looking a bit untidy, but this is a development aircraft. And here you have in front, you have the cone and you have the radar housed inside it. It is a single seater. It carries 2.4 tons of internal fuel and 13.2 tons is the maximum all-up weight, giving it a payload carrying capacity of 3.5 tons. Now, one of the criticisms leveled against the project is it took 35 years, and so why did it take 35 years? So I'll just go through that. The Cabinet Committee on Political Affairs gave its approval for the development of the LCA on 16 July 1983. Please remember this date, July 1983. The Aeronautical Development Agency under the Ministry of Defense was registered as a society under the Societies Registration Act 1860 on 16th June 1984. The first Director General was Dr. S.R. Valluri, Dr. Sitaram Rao Valluri, who had been the Director of the National Aerospace Laboratories for the previous 19 years. From 1965 to 1984, he had been the Director of the National Aerospace Laboratories and one of the doyens of the Indian aerospace community. The program was formally launched by the Raksha Mantri P.V. Narasimha Rao at the first General Body meeting at Bangalore on 30th January 1985. And a financial sanction of 560 crores was accorded at this meeting. The Indian Air Force issued the Air Staff Target Air Staff Requirement 2 of 85 for the LCA in October 1985. Then in December 1985, Dr. Valluri resigned because of some differences he had with the scientific advisor at that time. And Dr. Kota Harinarayana was appointed Program Director and Chief Designer in January 1986. Dr. V.S. Arunachalam, the scientific advisor to the Raksha Mantri, was also the Director General of the Aeronautical Development Agency. Now I'll show you a bigger picture of the one in the corner. Now, I would say that these three men are the architects of the program. Here you have Prime Minister Rajiv Gandhi. You have Chidambaram here, but he didn't have anything to do at that time. Dr. V.S. Arunachalam, the scientific advisor, and Dr. Kota Harinarayana, the small man with the great heart. So what really happened was that in the early 80s, when the LCA was being spoken about, the search went on for an engine because we did not have an engine. Team of scientists led by Dr. Valluri went to Europe, and they tried to get the RB199 engine, which was being used in the Anglo-German Tornado aircraft. It was not available to us. So on his return to India, Dr. Valluri mentioned this to R. Venkatraman, then Raksha Mantri, and he went to the Prime Minister, Mrs. Indira Gandhi. She was still in office. And she said, why don't we approach the United States? So that was an act of great political courage because the relationship between India and the United States was very frosty after the 71 war. And Dr. Arunachalam went to the US and met Mr. Caspar Weinberger, the Defense Secretary of the United States. Mr. Weinberger was very thrilled that India was embarking on such an ambitious project without the involvement of the Soviet Union. So with this background, when Prime Minister Rajiv Gandhi went to the United States in 1985 on an official visit, he established a very good relationship with President Ronald Reagan. And when he asked President Reagan for help with the LCA program, President Reagan readily agreed. And therefore, US technology, the door of US technology was open to us, and we made full use of that opportunity. Now, Dr. Kota was only 43 years old when he was appointed in 1986, and he had enormous enthusiasm and drive, and he had the difficult task. Aeronautical Development Agency was a greenfields project. He had to assemble the engineers, he had to build relationships with public sector units, the academia, and the private sector. And Dr. Kota did a great job, and I think These are the three people who are the real architects of the program. Now, how do you create a design team from nowhere? So Dr. Kota went to Chairman HAL, Air Marshal Wallen, asked for some engineers to be attached to him. So immediately Air Marshal Wallen gave him 200 engineers. Kota added more engineers from DRDO, ISRO and NAL, and Team LCA consisting about 300 engineers was formed. Dassault Aviation of France was chosen as a partner for the project definition phase, the PDP. And the US F404 engines was chosen. It was made available to us. And we bought 11 engines at that time at the cost of $1 million each. 30 French engineers came to Bangalore and worked with Team LCA for one full year from October 1987 to October 1988. And they produced a 1,000-page report. This 1,000-page report was sent to Air Headquarters. Air Headquarters in turn went through the report and they felt that the time frame and the cost indicated in the report could not be met. They said it will take much longer and it will cost much more. Therefore, they wanted a technology demonstration program to be run first. As I told you earlier, the external configuration was chosen as a compound delta wing, and the new technologies which were chosen to meet the air staff requirement, I'll show you in the next slide. In the aerodynamics part of it, unstable aerodynamic configuration, longitudinally unstable aerodynamic configuration was chosen to make the aircraft more maneuverable. So the new technologies which were required to be incorporated in the aircraft was a fly-by-wire flight control system. We'll talk about it a little more later. The glass cockpit where all the round dial instruments would be removed and you'll have only display screens. Composite materials in the airframe and computerized monitoring of health monitoring of systems. The IAF insisted on a technology demonstration program. Despite political instability and financial crisis in the country from 1989 to 1993, work to generate the aerodynamic database to build a mathematical model of the aircraft started in 1991, using 5 wind tunnels in the United States, 2 in the United States, 1 in France, 1 in Russia, and 1 in India at the National Aerospace Laboratory. The big wind tunnel used in the United States was at the Arnold Engineering Development Center, AEDC in Tennessee. That is where we sent the 1/6 scale model, and the bulk of the aerodynamic database was built in that wind tunnel. Now, you all remember that in 1991, India went bankrupt. We had to pawn our gold to stave off defaulting on debt repayments. And by the time things settled down and the financial sanction for 2188 crores for the tech demo program was given, it was June 1983. Please remember the CCPA sanction was given in July 1983. And here 10 years have already gone before we could even get down to working properly on the project. Now, the mandate given for the tech demo program was to have 2 demonstrator aircraft and 1 structural test airframe. They were to be manufactured by Hindustan Aeronautics, which was the principal partner. A flight test program of 200 to 220 flights had to be flown to prove the new technologies. And the flight testing infrastructure was supposed to be set up. So the National Flight Center was set up in September 84 by me when I came on deputation to the Aeronautical Development Agency from the Air Force. Now I'll just spend a little time on this fly-by-wire. The technology chosen was quadruplex digital fly-by-wire technology, which was offered by the United States. Dassault Aviation, who had partnered us in the project definition phase, was hoping to be chosen as the partner for the tech demo phase. But when we chose the American system, they walked out of the program. As a result, the decision was made to go it alone without a full-time partner. Now you have, what is the fly-by-wire system all about? You have, can all of you see the full diagram? You have the pilot, you have the pilot's control column.
We can see that.
Yeah. The control column movements are converted into electrical signals and goes into a digital flight control computer. The computer sends electrical signals to the actuator, which moves the control surface, which in turn alters the aircraft aerodynamics and forces and moments. And the aircraft dynamics is fed back to the pilot. It is also fed back through motion sensors, rate gyros, and accelerometers back into the flight control computer. So the flight control computer knows exactly how the aircraft is behaving at any one time. And the flight conditions are picked up by the air data sensors, and that is also fed into the computer. Now, between the motion sensors and the flight control computer, in this input, we have something called the notch filters, which filter out undesirable frequencies caused by aeroelastic distortion of the airframe during maneuvering flight. That's very important. Without the notch filters in place, you'll get all kinds of wrong inputs going into the flight control computer, and you will not get the desired output here. Now, the flight control computer has two main things. One is called the control law, which decides on how much control deflection will take place for a particular input of the pilot, depending on flight condition. And the other half has housekeeping functions like redundancy management and actuator management and channel management and so on. And the warnings and other information of the flight control system is put out on the screens in the cockpit for the pilot to be aware of what's going on. And therefore, there is a link between the flight control computer and the mission computer of the aircraft. So there is a very close, it's called the integrated flight control system, which has the digital flight control computer and the mission computer all linked together. Move on to the next slide. The fly-by-wire development, even with the initial grant of 560 crores, development work started in right earnest in 1992 itself. Agreement was signed with Lockheed Martin of the United States. Of course, it was under a different name at that time, but it is now Lockheed Martin. And Dr. Kalam constituted a national control law team with scientists and engineers from the National Aerospace Laboratories, the Aeronautical Development Agency, Aeronautical Development Establishment, Hindustan Aeronautics, and the Indian Air Force. Now, when we're talking about the control law is the intelligence which controls the control deflections which the pilot demands and which is modified by the control law and the computer, depending on flight condition. And the amount of control deflection is called the gain. And the control input, if it goes in phase with the aircraft, it's called in phase. Otherwise, it goes out of phase. Therefore, the control engineers have to tailor the control law to maintain gain and phase margins. Now, you will appreciate that at low speeds, when the dynamic pressure on the control surfaces is very low, the large control deflections are required. If the same large control deflections are applied at high speed, it will break the aircraft. So the gains, control law gains have to be very carefully tailored depending on flight condition. To do all this, the control engineers made extensive use of modeling and simulation. They built a small elementary simulator at NAL itself, and the Indian Air Force and the test pilot was attached full-time to the control law team. And as the control law was being developed, he would try this control law out in this elementary simulator called the ELS. It was called the Engineer in Loop Simulator. ADE, the Aeronautical Development Establishment, developed a full engineering simulator, and test pilots from the National Test Flight Center went and evaluated the control law as it was evolving. The entire digital flight control computer hardware and software was developed by the Aeronautical Development Establishment, and they did a marvelous job of that. And the actuators, the hydraulic actuators, which actually moved different control surfaces, and the sensors, the rate sensor assembly and the accelerometer sensor assembly, the source from the United States through Lockheed Martin.
Sir, there was a question if you could elaborate a little bit more on particularly on the sensors and methodologies employed in the fly-by-wire technology, the figure that you've shown in the previous slide.
Can I also ask a question just now? The simulators and the simulation that you refer to on this particular slide, are they essentially only software, or are they also hardware items which are tested out inside a wind tunnel?
I'll answer the simulator question first. It is online simulation. The pilot sits in the simulator. He's got a full cockpit within throttle, and the engine model is also incorporated. And then the mathematical model of the aircraft is flown using computer generated imagery, and it is very realistic, and it is able to assess, the pilots are able to assess the handling qualities of the aircraft sitting in the simulator. So it is online, hardware and software all combined. Now, regarding the earlier question regarding the control law was developed by control engineers sitting in the National Aerospace Laboratory, Flight Mechanics and Controls Division. And as I said, as the control law, the control engineers themselves did not have too much of an idea of how the aircraft flew. That's why we put a test pilot there, and he tried out the control law as it was being evolved. And then when it reached a certain stage of development, it was transferred to the engineering simulator at ADE, where the NFTC pilots went and refined it further. So that was the methodology adopted for the control law. There's still some more to come, so I'll just carry on. Once the control law, the hardware and software integration was done initially by at Aeronautical Development Establishment, ADE, they developed an integration rig called the Mini Bird to check out the integration. The Mini Bird had only one of the L1 actuators in the loop. So when they were satisfied that the integration was satisfactory, they moved it to another big facility called the Iron Bird. The Iron Bird was built by Hindustan Aeronautics, and this is where the main system validation was carried out. Now, let me spend a little time on the Iron Bird. The Iron Bird is a huge delta iron frame. You can see this thick iron frame. It has all the control simulated here. This weight here simulates the L1. And then you had the undercarriage. You can see the wheels here, the undercarriage struts and the wheel. And you have the second wheel here, and you have the nose wheel, which is not visible. It's right there at the back. And the air brakes. both hydraulic systems were the same hydraulic systems which went into the aircraft, the same hydraulic pumps were used. The mission computer was modeled and integrated with this. And here again, the pilot sat in the cockpit with a rudimentary display and flew it. And when they flew it, you could actually hear the actuators moving, you could retract the undercarriage, you could assess what was the load on the hydraulic system. And a complete validation of the system was done before it was taken on to the aircraft. So this was a very, very important phase of the development. It was the Ironbird integration system.
But
okay.
was this tested in a wind tunnel?
Say again?
Was this system, it seems to me that it is primarily a software kind of system. Was it actually tested in a wind tunnel?
Yes, yes. The entire aerodynamic database on which the control law was designed and the aircraft mathematical model was created, all the aerodynamic data was generated in wind tunnels. I told you 5 wind tunnels around the world were used. All the wind tunnel data was normalized by the aerodynamics department at Hindustan Aeronautics. And then the aircraft model was created. It was also supplemented a little bit by computational fluid dynamics, CFD. As flight testing went on, when the aircraft really started flying and we started getting real world data, this model kept getting updated. Yes, without the use of the wind tunnels, we couldn't have even started the process of developing the control law. Now, after we evaluated the control law and the engineering simulator at ADE, the next step was to go to the United States to a company called CalSpan at Buffalo, New York. And we tested the control law in 1994 December, June of 1995, and July of 1996 on these 3 aircraft, the Learjet, the T-33 trainer, and the F-16. We did something like 400 landings on these 3 aeroplanes. The most realistic one was the F-16. Now the in-flight simulator aircraft is able to simulate the handling qualities of the control law which is being tested by mimicking the initial response of the pilot input. The initial response of the control input mimics the exact initial response of the actual aircraft, and therefore the pilot is able to assess the handling qualities, because the handling qualities are assessed mainly on the initial reaction of the control input. And of course, you cannot evaluate it in the entire, the Learjet and the T-33 trainer have a small flight envelope, and you can only evaluate the control law within the limited flight envelope. Whereas in the F-16 trainer, we were able to go to a bigger envelope and we were able to do more complex tasks like close formation and tracking of a target using a gun sight. Now, this is me standing in front of the F-16 aircraft at CalSpan, and this is CalSpan test pilot John Ball who flew with me. And at the end of it, we made an assessment of the control law using something called the Cooper-Harper rating scale. This is a qualitative evaluation tool, and here it is. So right at the bottom, you have is the aircraft, the pilot's decision, is the aircraft controllable? If the aircraft is not controllable, then improvement is mandatory, and therefore this is given the number 10. So like that, in various deficiencies, you move up, and the deficiencies require improvement. You have major deficiencies, adequate performance. The various qualitative criteria which you can read on the screen. Now, sitting in NAL, the first test pilot would bring the control law to somewhere to this standard. That is level, the first three are called level 1, the next three are called level 2, and the third is level 3. From level 3, you'd bring it to the top of about level 2, and then hand it over to the national NFTC test pilots, who would try and refine it further and try and take it somewhere into level 1, second category before we got airborne. And once you start flying, you do further refinement and try and take it there. The Tejas is not quite there as yet. It is probably sitting somewhere here. And they are very hopeful that it will reach level 1, category 1 with a little more development. So this was a very, very useful qualitative assessment tool, which was extensively used by the test pilots to assess the control law. We did, as I told you, 400 landings on the in-flight simulation aircraft. We flew something like 1,500 hours on the AD simulator, and we did about 2,000 landings on the AD simulator, even before we went for in-flight simulation. So extensive work was done to make sure that the control law was behaving properly, that the aircraft was controllable right through the flight envelope. And that's how the fly-by-wire system got developed. And remember, please remember that all this was being done for the first time in India. The next big technology that was incorporated in the LCA was carbon composites, the use of carbon composites in the airframe, which was also being tried out for the first time in India. The technology was developed by the National Aerospace Laboratories and later transferred to HAL and the private sector, Tata Advanced Systems Private Limited. ADA, under the guidance of Dr. Kota, developed a software tool called AutoLay, which was used to lay up the composite material comes in sheets called pre-pregs. It's impregnated with resin and laid one on top of each other. And this software was assessed by Airbus, and they even bought a copy of the software which they used for their manufacturing activities. The composite wings, the wings were entirely composite, and this was designed and developed by a national wing team of NAL, ADA, and HAL personnel. Now, this national team concept, Dr. Kalam created these 3 national teams. One was the National Control Law Team, the National Wing Team, and the National Flight Test Team. So these were the 3 managerial, achievements of Dr. Kalam when he brought together people from diverse agencies and made them all sit together and work for a common program. Now, everything was going very well till May 1998, when India exploded the nuclear devices at Pokhran 2 tests. And the very next day, the Western world, led by the United States, imposed technology sanctions, and all interaction with US companies ceased overnight. Our AD engineers were working with Lockheed Martin in the United States, were sent back. They were not even allowed to take their notebooks back. Some hardware which AD had sent to Lockheed Martin was also impounded. The General Electric service engineer was looking after the GE404 engine was recalled. He left, and we were badly affected. The LCA program was badly affected. Also, the other big problem we had only 3 sets of actuators with us, one which was used in the first technology demonstrator aircraft. The second one was on the Iron Bird, and the third set was being used by the certification agency. They're strip examining it to certify it fit for use. So we literally were living hand to mouth, and we only had one good set of actuators to manage. But the decision was taken to go ahead with the program. Post-Pokhran, the decision was made to fly the technology demonstrator aircraft with available resources. An indigenization program for critical line replaceable units was also launched. Now, I'm very happy to tell you that many of the items which we started indigenizing at that time have now been indigenized and certified, and they are flying on the aircraft. It greatly improved our self-reliance. Now, the aerodynamics of the configuration was unstable. So the decision was taken to develop a new control law to fly it in a limited envelope with reduced instability. The full-scale integration work of the flyby system on the Iron Bird was commenced in late 1998. It was offered for pilot and loop tests in November 99. So the pilots went and sat in the Iron Bird and they flew the aircraft, the model aircraft, using all the hardware in the loop for 1 full year. And they completed a matrix of tests designed to expose weaknesses in the system. This matrix of tests was developed by the control law engineers and the test pilots and the test engineers working as a team. And a number of software changes were asked for, about 11 or 12 software changes were asked for as the testing progressed. The tests were completed in November 2000. The first technology demonstrator aircraft was extensively instrumented, 1400 parameters, of which 400 were telemetered down. A telemetry ground station was set up at NFTC. The first engine ground run was done in April 1998 with the full instrumentation on board. And this engine ground run was used as an opportunity to debug the instrumentation system and make sure everything was working properly. The taxi test commenced in February 99. The brakes and the nose wheel steering mechanism were checked out. The brakes were a new innovation called brake-by-wire that was also controlled by a computer. Both the brakes and the nose wheel steer were controlled by a computer. It was called brake-by-wire. And the carbon-carbon brake discs were developed by a DRDO laboratory for the first time in Hyderabad. And then modifications were asked for acceptability by the test pilots. Initially, they were very unhappy with the quality of the braking that was available. So a lot of work had to be done to make the aircraft fit for flight. Now the pilots had to be trained to fly. So I went to Air Headquarters and asked for the allotment of a Mirage 2000 trainer for flying practice for the test pilots. The Mirage 2000 trainer arrived in May 2000. Now, the first few flights of the technology demonstrator was supposed to be flown with air data system, which had not been processed by the mission computer. So the airspeed and the altimeter, the height and airspeed were raw data which was being picked up by the air data system. So that had to be calibrated, and we used the Mirage 2000 to calibrate it to make sure that the Mirage 2000 system itself was, its pressure errors were known properly. We first calibrated the Mirage 2000 using the GPS, and then this was used as the master datum for the LCA air data system, first block of 12 flights. Now the control law, which requires accurate feedback of flight conditions, is called scheduled gains. And if flight conditions are not fed back to the computer, it is called fixed gains. Now, fixed gains greatly limit the flight envelope of the aircraft because of the need to respect gain margins. I spoke to you about gain margins. Next slide. Now, a word about the mission computers. The first mission computer, which was based on an Intel 386 chip. I hope you all remember the Intel 386 computers which we used. in the mid 80s. Foreign companies wanted 100 crores to develop this, but ADE developed it at a cost of 9 crores. The software was developed by ADA. It flew on the first 4 prototypes and never experienced a failure. Now, we had to have a more capable mission computer because of the requirements of the program. So from the 5th aircraft onwards, you had the Motorola 7410 PowerPC based open architecture computer, which was designed to cater to all operational requirements. The full glass cockpit eliminating all analog round-dialed instruments was implemented from the 4th aircraft onwards. The head-up display was developed by a CSIR laboratory called the Central Scientific Instruments Laboratory at Chandigarh, and it flew from the 2nd aircraft onwards. The computerized health monitoring systems were developed by the avionics engineers at ADA itself. So there you have all the 4 technologies which we wanted. That is the fly-by-wire, the composite airframe, the glass cockpit, and the health monitoring system. They were all put into the first technology demonstrator, and we flew it. We started doing high-speed taxi techs, but before that, the hardware and software of the flight control computer had to be installed on the airframe. And to do that, HAL had signed a consultancy agreement with British Aerospace. The first flight readiness review board was held on 24 December 2000. I was the chairman of the review board, and I gave the go-ahead for the first flight, having satisfied that all possible precautions were being taken. We did a successful first flight on 4th January 2001. This is a snapshot of Wing Commander Kotial piloting TD1 on its first flight on 4th Jan. The number here you see KH2001. KH stands for Kota Hari Narayana, and 2001 is the year of the first flight. All aircraft which fly in India either have to fly with a VT registration, civil registration, or it has to fly with the Government of India roundels here. So when I went to air headquarters, when I spoke to air headquarters, I said, give me a number. They said, no, we don't have it in our inventory. So we can't give you an Air Force number. So you do what you want. So I came up with this idea of KH2001, and I painted the roundels and we flew it. The chief executive of Lockheed Martin wrote to the Raksha Mantri, George Fernandez, not to permit the flight as the flight control system had not been developed with adequate rigor. Fortunately, the Raksha Mantri ignored the letter and he let us go ahead. He told us 6 months later about this letter. So on the 4th flight, TD1 did a flypast at Aero India 2001, which brought us a lot of positive publicity. The first block of 12 flights was completed by June 2001. And thereafter, TD1 was grounded because TD2, the second aircraft, was supposed to fly 9 months later, 9 months after the first aircraft. That means by September 2001, we should have flown the second aircraft. But we ran into problems with that aircraft, and we were able to fly it only with 2002. Now, the reason for this was that we had built the composite wings earlier, and a lot of sealant to prevent fuel leaks had been applied inside the tanks, but the tanks were left without fuel in it, and therefore the sealant started flaking and blocking the fuel filters, and therefore we had spent a lot of time cleaning up the whole system before we flew it. TD1 exceeded the speed of sound on the 1st of August 2003, becoming the first Indian-designed aircraft to go supersonic in level flight. Both aircraft started expanding the flight envelope to Mach 1.4. I hope we all are conversant with what the Mach is. The Mach number is the ratio of this true SP to the local speed of sound at the height at which the aircraft is flying. It is named after Ernst Mach, an Austrian physicist. Mach number is very important in aeronautics for supersonic flight. Then we went up to 50,000 feet altitude, plus 3 normal G and 17 degrees angle of attack. The technology demonstration program of 202 flights was completed on 31st March 2004, and no major problems were uncovered. This was a huge morale booster for all of us, and the government of India was very happy, and they flashed the green light to go ahead with the full-scale engineering development, full-scale development. The government gave the go-ahead in April 2004, though the first tranche of funding came only in November 2004. 4 more prototypes were authorized and 1 trainer version. So 5 aircraft were supposed to be manufactured. And due to lack of experience of the controller team and the flight test team and everybody else, the entire team LCA was very inexperienced. The flight envelope was expanded in the clean configuration without anything under the wings. It was taken to 1.6, 50,000 feet, altitude 6G and 24 degrees angle of attack. This took a long time. It took 800 flights and 4 years, because it had to be done very, very carefully. We didn't want to have an accident. And to expand the envelope, we had to do a lot of flutter testing. Now, what is flutter? Flutter is the dangerous interaction between aerodynamic forces and the aeroelastic bending and twisting of the airframe. Now, what happens is, under aeroelastic forces, the wing twists. And if the twist increases the angle of attack, the aerodynamic forces, the lift on the wing keeps increasing, and it can even exceed the structural strength of the wing, and the wing can break off. Many aircraft have been lost in flight due to flutter of the wing or flutter of the tail fin. So this is a very, very important test, and because of inexperience, the team had to proceed very cautiously, and I'm happy to say that we did not encounter any problems.
Can I ask a question?
Yes, please.
You mentioned the angle of attack, and the flutter is dependent upon, or flutter causes the angle of attack to change and all that. So
yes.
What is the kind of optimal kind of angle of attack that you would have under normal flight conditions or under combat conditions? And what are the similar kind of parameters for other well-established aircrafts, fighter aircrafts?
See, all aircraft have an angle of attack limit beyond which, if you go in a normal straight wing aircraft, the aircraft will stall. In a delta wing aircraft, the stall is not so well marked, but all the same, you will get into severe wing rock and you lose control of the aircraft. So all aircraft have a limiting angle of attack beyond which you cannot maneuver the aircraft. So in the LCA, the maneuvering angle of attack will probably be around 23, 24, though we have cleared it to 26. So this is an aerodynamic limitation of all wings. All wings have a stalling angle of attack beyond which the wing cannot be taken. And this is a limitation only in a fly-by-wire. To avoid inadvertent accidents of the stall angle, we put an angle of attack limiter. For example, in the LCA, you cannot go past the 26 degrees angle of attack limit. You will get a warning and the stick will move forward to reduce the angle of attack. Does that answer your question?
Yes, but are there similar limits for, let's say, F-16 or Mirage 2000?
Yes, every aircraft has this.
And they differ from combat conditions from normal flight conditions?
Yes. In combat conditions, before fly-by-wire, good pilots would be able to take it right to the limit and extract the maximum performance. That is what differentiated between a good pilot and a bad pilot. And once fly-by-wire came in, everyone was brought to the same level because you could extract the maximum performance without exceeding the limits because of the limiters in place. Right, now here's a shot of the LCA carrying external stores. So on the right-hand side at the wingtip, you have the close combat missile, the R-73 over here. This is a 500 kg bomb being carried on the midboard station. You can either carry a bomb, a laser-guided bomb, or you can carry beyond visual range missiles. Here's the drop tank. Drop tanks inboard, and the same thing on the other side. And here we have another station where we carry the target designation pod. The target designation pod is carried here, and here you have an internal gun. So this is the payload carrying capability of the LC. I told you it carries an external load of 3.5 tons. Okay, now once we started expanding the envelope, we had to do a lot of environmental testing to clear the aircraft for hot and high tests. We went to Leh, and this is a fine shot of the LCA getting airborne from Leh. This is probably taken in the month of December because all the hills are snow covered. And hot weather trials were done at Nagpur and Jaisalmer. And environmental testing took a lot of effort. And one thing we did was no test of the LCA was ever done without telemetry. We had 2 telemetry systems mounted on trucks. And whenever the LCA had to go to an outstation, these trucks would proceed a few days earlier and position themselves. And all flying was done under telemetry. Dedicated BSNL line would be used to transmit the data back to the designers at Bangalore, and designers sitting in Bangalore could monitor exactly what was going on during the test flight at whichever location, whether it was Nagpur, Leh, Jaisalmer, Goa, or Chandipur on the East Coast. So every single test flight done was under telemetry. Now, radar and sensor integration, we use the Israeli multimode radar 2032 because our own radar was not ready. I'm happy to say that the active electronically scanned array radar is undergoing flight testing. So this is a temporary measure. We have, and it was the ELTA 2032 was modified to suit our Indian Air Force requirements. Radar testing took considerable flying effort to prove almost like air-to-air, air-to-ground, ground mapping, etc. Then we had integrated lightning laser targeting pod, which is required for laser-guided bomb release. And this was also sourced from Israel and integrated. Then we had a helmet-mounted sight and display, HMDS, which is also sourced from Israel and integrated. And we used initially the R-73 Russian missile, and later the Python 5 Israeli missile. Now, since this whole thing we deliberately chose all this from a single source, Israel, because of ease of integration. Of course, now the radar will be ours. These things, we have already developed a beyond visual range missile, and gradually everything is getting indigenized. Here is a shot of the LCA launching the R-73 close combat missile. This is off the coast of Goa. In this way, we achieved initial operational capability in December 2013. And in January 2016, the two Tejas aircraft were taken to the Bahrain Air Show. They flew over the sea from Jamnagar to Oman and from Oman to Bahrain. And it had made a very favorable impression at the Bahrain Air Show. Then we had the first IAF squadron was formed on the 1st of July 2016. And now it is up to full strength. For final operational capability, FOC, a beyond visual range missile, had to be integrated with air-to-air refueling had to be done, and an internal gun also had to be integrated. And flight envelope had to be expanded to 8G and 26 degrees angle of attack from the earlier 6G and 24 degrees angle of attack. This was achieved in February 2019. Now, this is a shot of the air-to-air refueling. Tejas doing air-to-air refueling from an IL-78 tanker. And to do air-to-air refueling, a few things had to be done first. First is the design and integration of the aerial refueling boom. Now, fuel is transferred under pressure from the tanker. So pressure refueling, the whole fuel system had to be made fit for pressure refueling. A lot of changes in the fuel valves and so on had to be done internally. And also for static electricity discharge, the electrical grounding of this probe had to be very carefully done. And since the engine will be running when the refueling is going on, we first had to do something called hot refueling tests on the ground, where usually an aircraft is refueled on the ground, the engine is switched off. But we had to do hot refueling with the engine running and the pilot sitting inside, because that was what was going to happen in the air. So with all that, we were successfully able to train the pilots. Incidentally, this boom and drogue and everything was simulated in the engineering simulator, and pilots did a lot of practice on the simulator before going up and actually hooking onto the tanker in the air. Next, I'll say a few words about the carrier naval aircraft program. The naval LCA was sanctioned in 2005, and a consultancy agreement was signed with the United States Navy in 2012. And the United States Navy gave us considerable help in achieving the first carrier landing in January 2020. The first prototype was a two-seat trainer with improved over-the-nose visibility for deck landing. The airframe and undercarriage were strengthened to withstand the no-flare, high rate of descent deck landings and arresting wire loads on the tail hook. Now, the normal rate of descent, vertical rate of descent for the Air Force version is 10 feet per second. That is about 3 meters per second. Vertical rate of descent. The undercarriage is designed for that. Whereas for the naval version, we had to strengthen it to withstand 21 feet per second rate of descent. Very high rate of descent. The aircraft just slams into the deck, and all that, the hook loads, the landing loads, everything has to be reacted through the airframe itself. To do this, the first naval version flew in 2012, and then we set up a shore-based test facility, SBTF, at INS Hansa at Dabolim in Goa, just south of the main runway. The same Russian arresting gear used on the Indian aircraft carrier, the INS Vikramaditya, was installed and extensively instrumented. We put a lot of video cameras to capture the whole landing sequence and the hook loads and so on. Ski jump takeoff was also installed at the western end of the shore-based test facility. The ski jump is a parabolic ski jump with a 14-degree angle, 14.3 actually, at the SPTF. And I will show you a photo of, here's a dramatic shot of the LCA, the naval LCA leaping off the ski jump facility at Dabolim in Goa. You can see the main wheels are still down, and then the close combat missiles are being carried on the outboard station. And
Quick
over
question.
here, you'll see say again.
Quick question. Why did you say 14.3? Is there something special about that 0.3?
Well, I think the aim was to get 14 degrees, but actually what was there at 14.3. But the aim is 14 degrees, correct? The Indian aircraft carrier, which has been made at Cochin, has got a ski jump at 14 degrees. Here you will see a slight difference in the aerodynamics of the aircraft. You have a surface, additional surface here. It is called the LEVCON, Leading Edge Vortex Controller. I'll talk about it in a minute. Now here is the Naval LCA grabbing the wire at the SBTF at Goa. You can see the impact, the viciousness of the impact. You can see how the oleos are compressed. You can see the smoke coming from the tires, and the hook is all set to grab the wire. And the leading edge vortex controller, the LEVCON, is deflected fully up. Now, this is the whole aim of this aerodynamic surface here, is to reduce the approach speed so that the arresting load on the hook is reduced. So this required a lot of aerodynamic tuning. At the moment, it is manually operated. It is going to be made fully automatic by the fly-by-wire system in the subsequent models. And these are the leading edge slats, which are also being operated by the fly-by-wire system. Full-fledged telemetry station was set up. Video cameras were installed to capture ski jump and arresting characteristics. First ski jump was performed by the first naval prototype in December 14. Indian Navy test pilots and engineers were trained by the US Navy at Patuxent River in Maryland, in the USA. The second naval prototype flew in February 2015. Extensive preparatory work was done at the SPTF Goa. Day and night ski jump takeoffs were performed. Taxiing arrests were performed at varying speeds. And then the first arrested landing was done at the SPTF. This one, the first arrested landing was done in September 2019. Thereafter, on 11th of January 2020, that is last January, NP1, the naval prototype, went and trapped on the deck of the INS Vikramaditya, which was cruising off the Karwar coast in the Arabian Sea. And this was a great landmark in naval aviation, because for the first time, we had an Indian aircraft landing on an Indian Navy carrier, entirely home built. And here I want to point to one man standing here. He's called the landing signals officer. He controls for every single landing and takeoff on the carrier. The landing signals officer is the ultimate authority, and he is in radio contact with the pilot. And he is the one who says you're clear to land, or he waves it off. He says, no, your approach is not looking good. You go around and come again. So this landing signals officer was trained by the United States Navy. Two of them were trained there how to go about this very onerous duty. And the United States, the help provided by the United States Navy was crucial for achieving this milestone. The next day, the carrier, the LCA, did a ski jump off the carrier in the Arabian Sea. And on the Vikramaditya, it turns out that the ski jump was at 13.75 degrees. It was not 14 degrees, but we still did it. Now, in all this, the Center for Military Airworthiness and Certification played a very important role. The Directorate General of Aeronautical Quality Assurance played a major role in overseeing the manufacturing process. 300 private sector industries contributed their products. And the biggest role, of course, was played by Hindustan Aeronautics. They are the principal partner. They did the diesel design and manufactured the aircraft. So I would say that the LCA program was a huge symbiotic effort between Hindustan Aeronautics, DRDO, ADA, IAF, NAL, private sector industries, public sector industries, and foreign consultants. Thousands of men and women have participated in this program. That's why I've not named anyone in particular except a few important players like Dr. Arunachalam and Kalam and Dr. Kota, because there are far too many people who have contributed their might to the success of this program. Now, the National Flight Test Center, which was set up in September '84, we were given the mandate to carry out safe conduct of the technology demonstration phase. This was me in the cockpit of the Hawk trainer in the UK in 1986. It was a small focus group of about 25 people consisting of test pilots, test engineers, and scientists. Flight test is the last link in the chain where a major accident or incident can be prevented. Extensive use was made of simulator training and telemetry monitored conduct of test flights. It was all about doing things safely, doing dangerous things safely. Now, a lot of criticism was leveled against the program, saying thousands of crores have been wasted and the whole program is a waste of time. So I'd just like to clear the air on that. The total financial outlay for the project from the first tranche in Jan 1985 till 2020 was 14,293 crores. You divide that by 35 years, you get about an outlay of 408.37 crores a year. Now, with this kind of an outlay, 17 aircraft were used for the test program. 5,000 test flights were flown without a single incident or loss of aircraft, a record in the history of Indian fixed-wing aviation. Aeronautical technology has received a major boost. Aeronautical ancillary ecosystem has evolved, and the Tejas program was a success story. I have one more slide. This is a slide dedicated to the women who have played a major role in the program. These are the senior women scientists at ADA. All of them have made a major contribution to the program. There are others in NAL, in HAL, and in industry who have all contributed. So I just want to say that the Tejas program was a gender-neutral program. Women and men have played an equal role in the success of this program. I have finished. Thank you very much for your patience.
The fantastic lecture, sir, Marshal Philip Rajkumar. I think very rarely one hears such kind of talk, which is a grand mix of the technology. And as you grew from mid-1980s till now, and also, justifying and talking about some of the things what we keep hearing about the budget and the delays and so on. And also these, when one develops such a strategic systems, the hurdles that one face in terms of the country's, denial of, the corporations and so on, and still heading fast. And when you look now and go back and see what are all things happened in a particular ecosystem, in this case, it is about the aircrafts, combat aircrafts development. So it's a fantastic talk, and I think it's very rarely one covers such a vast area and still giving great insights into technologies. So, I mean, I don't have more words to describe this talk, but without taking more of your time, and also I think the many participants want to ask questions. Please go ahead. I see okay, there are quite a few of them. Let me start with Sandeep, Professor Sandeep Trivedi.
Thank you, Satya. Well, first of all, thank you very much, Air Marshal Saab, for a very inspiring talk. And I think I speak for everyone. We felt very proud to hear about your accomplishments and all the many, many men and women and so many organizations which have just made India so proud. Thank you, sir. I've just two quick questions. One is, could you give us a sense for the extent of deployment of the LCA, which is being planned both in the IAF and in the Indian Navy, so we get a sense of how the aircraft will be used in the future or near future? And the second is, I think you mentioned this in passing, but it would really benefit us if you could elaborate. The engine of the Tejas, I believe, is still the GE engine, which will be purchased from the United States. And I have learned in other fora as well that somehow India has not developed a capability more generally to be able to manufacture jet engines. Could you please elaborate a little bit more on that general question, whether there are any plans for the Tejas in the future?
Yes, along with the Tejas development program, jet engine development program to develop the Kaveri engine was also launched. The Kaveri engine was developed and it flew 57 hours in a flying test bed in Russia. And unfortunately, after 57 hours, it had a small problem of compressor rub on the casing. And therefore, the team brought the engine back, and then in the idea, the Kaveri program was short closed, which in my view was not a very good decision, because if we had gone ahead by now, we should have flown that engine in a single engine aircraft, developed confidence. And so right now there are talks going on between India and foreign companies, mainly Rolls-Royce, to develop a 110 kilonewton engine. And in the meantime, Hindustan Aeronautics Limited, their engine design bureau, they've already designed a 25 kiloton jet engine. They're also designing a turboshaft engine for helicopter use. So things are moving along, and the problem is that the hot end technology, the high temperature end of the jet engine technology, foreign companies have spent billions of dollars and they consider it their crown jewels of technology, and they're not going to give it to you, whatever they might say. So we have absolutely no choice but to follow the difficult route and develop things ourselves, which requires a huge investment. So I do hope that in the years to come, the government will make the necessary investment and we will be able to produce our own engine, because in my view, unless we have our own engine, we cannot call ourselves fully self-reliant. So that was your question regarding the engine. What was the earlier question?
Sorry, if it is possible to give us a sense for the scope of deployment of LCA, that is, how many such aircraft is it being planned that the IAF and Indian Navy will use? I mean, if it's possible in the public domain, just so we get a sense for how many squadrons will be raised, or what is the extent of usage.
So the initial order was for 40 aircraft. Of the first squadron which was formed in the IAF was formed with 16 aircraft, and the second squadron is also being equipped now. And so these 40 aircraft will form 2 squadrons. A further 83 aircraft have been ordered with Hindustan Aeronautics. Deliveries will start from April of 2024, they say. Now this new model, which is called Mark 1A, has an active electronically scanned array radar. It also has capability to have an external electronic warfare suite, and it is 83 aircraft will give us about 4 squadrons. So 4 into 6 squadrons, at least we will have, if not more. Probably more aircraft will be ordered by the Air Force. But as it stands, it is 4 plus 2, 6, or maybe 7 squadrons. The Indian Navy, of course, said that the LCA, the naval LCA as it stands, is too underpowered to lift a useful payload off the deck. So they want something called the twin engine deck-based fighter, TEDBF, which is under development at ADA. So whenever that comes, I suppose the Indian Navy will order 40, 50 aircraft of those. But then all that is critically dependent on our success in developing this 110 kilonewton engine.
Okay.
Thank you very much.
Yeah. Thank you, Professor Sandeep. Yeah, there are quite a few more questions. So let us quickly move to Alak. Can you ask a question quickly?
Very wonderful introduction for us, and congratulations. I have 2 questions, which is kind of similar to that was asked by Professor Sandeep. What kind of range and capability of these aircrafts are under actuality? From your payload capacity, is it? Am I correct in understanding that it might even have a strategic role? Number 2, you mentioned the number of aircrafts that might be available to Indian Air Force and Navy. But, approximately how many years we will be completely self-sufficient in terms of our requirements from indigenously manufactured aircrafts? And do you envisage also that we might be in a position to export these aircrafts?
Yes, there have been inquiries made for the Tejas aircraft from countries like Malaysia, and recently I saw in the papers that even Argentina has expressed some interest. But the manufacturing capacity of Hindustan Aeronautics is 16 aircraft per year. So even to meet this existing order of 83 aircraft will take 5 years plus. Also, we use bought-out equipment. The engine is American, and then the ejection seat we've got from the UK. So unless these countries allow us to export, we will not be able to export. You can truly say we are ready to enter the export market only when we have indigenous equipment everywhere, which is not the case right now. So right now, I am quite skeptical about the export orders fructifying. And regarding your question regarding the range, I wouldn't like to talk too much about it because those are all operational information. But suffice it to say that the LCA does not have a strategic role. It has a more limited role of air defense, interception within national airspace, and close support to the armed forces in the tactical battle area. Those will be the main roles of the aircraft.
Sir, before I let other questions, I want to ask you, you are already on the call for an hour and a half. Is it okay? Can you take 1 or 2 more questions, or we can?
Yes. Please go ahead.
Okay, so I'll try to limit to maybe 3 questions maximum. Let me go with Professor Vivek Datar.
Okay, some of the questions have already been asked by Sandeep and Alat, but I would like to know what is the rough time scale for the development of an engine. Of course, it has to be rough because there will be problems and they would have to be solved with indigenous technology. But what is the rough time scale?
Time scale for what?
For developing an engine for Tejas.
Oh, engine for Tejas. I would, since we have built up a base with the Kaveri engine program, I would say 10 years.
Okay.
Uh,
That would presumably provide, an impetus to even better, versions of that engine and, advances later on.
Yes, yes. I would like to just point out what the Chinese did. When we first got the MiG-21s in the mid-60s, we got an engine called the R11, which had a time between overall of only 250 hours. Every 250 hours, we had to send it for an overhaul. Whereas the Western engines all had a TBO of around 1,000 hours. But the Russians went ahead and made engines, even though they were not as good as the West, but they still had their own engine. Now, when the Chinese started manufacturing the MiG-21, they developed an engine called the WP2, produced it, put it into aircraft, exported the aircraft, but it had a TBO of only 200 hours. Now, I had an opportunity to fly this aircraft in Iraq, this Chinese aircraft, and it was a strange experience because I was sitting in a cockpit with all the captions in Mandarin. And I was able to fly it only because the cockpit was identical to the mark of the MiG-21 I was flying in Iraq. So this is it, we are too ambitious. We should produce whatever we have, put it into production, put it into service. Huge lessons to be learned. But we never seem to be going the full distance. We always stop short. And so the jet engine development story is not a very happy one.
Who is, by the way, in charge of this jet engine development? Is it ADA or is it HAL?
ADA has got nothing to do with it. It is Gas Turbine Research Establishment, which is a lab under DRDO headquarters. And you have another quite a capable design capability in the HAL Engines Division Design Bureau. Two of the small gas turbines which are flying today, one is called the PTAE-7, pilotless target aero engine 7, which is being used in the Lakshya target aircraft. That is developed by the HAL Engines Division. The jet fuel starter, which is used in the Tejas, which is a gas turbine based starter, is also developed by the HAL Engine Design Bureau. Now, HAL Engine Design Bureau is also developing this 25 kilonewton engine, which I spoke about, which will be used in the Sitara trainer if that goes into production. So we are moving along. All is not lost, but I don't think we have pushed it hard enough. Maybe because of lack of resources, it is extremely capital intensive. But our designers and engineers certainly have the capability to move forward.
Okay, thank you very much, Professor Tata. There's one question from Ullas. Ullas, if you want to ask yourself, or otherwise I'll read this question for you. Okay. Okay, the question is, how does Tejas compare with MiG-21 and JF-17?
With the MiG-21, it is a no contest. The MiG-21 is a 1960s generation aircraft. It has outlived its usefulness, and the Tejas is far superior in every metric that you can think of. In terms of technology, in terms of capability, in terms of payload, in terms of range, everything, it is far superior. So that is question number one. The JF-17 the first versions were not as good as the Tejas, but they're also improving continuously. And but I still believe that the Tejas will be more than a match for the JF-17.
So one last question, if I can ask. This is from the YouTube participant by name Anurag Bose. The question is, please say something about F-22 Raptor.
F-22 Raptor is the world's best fighter at the moment. The United States spent enormous amount of money in billions of dollars in development costs. And it is the most superior aircraft in the entire world. And it has got stealth characteristics. It has got the ability to track aircraft at great distances. It has got missiles which can bring down aircraft at great distances. And it has got communication links which are top secret. And nobody knows too much about it because the United States doesn't publicize too much information about it. But it is rated to be the world's finest.
Okay, I think there are no more questions, but also I think we are almost, as I said, an hour and 45 minutes long in this. But we never felt that we are actually in this such a long talk and so much of interactions, and more importantly, the quality of the talk and also the technology that you showed us and told us into, because many of us have no clue and no idea about what it actually takes to develop such a complicated technology, top-edge technology project. So once again, on behalf of the Asset Forum and also, in fact, all of us at TIFR, it is our great pleasure and great honor to listen to you today. And thank you very much, Air Marshal Philip Rajkumar. And at the same token, I also want to once again thank Professor Vivek Datar for being responsible for organizing, for bringing this talk a possibility. So thank you very much. With that, we would like to thank you once again.
Yeah, before I leave the meeting, I want to mention, I forgot to mention this, in the mission computer itself, you have something like 3 million lines of code sitting in it. And all that code was written and developed right here at ADA. And inside the flight control computer, you have another million lines of code. So the software inside the Tejas is about 4 million lines of code sitting there, all developed, verified, validated, and it is our intellectual property. It is Indian intellectual property. So that is an important point which I missed out. So that is another very heartening piece of information as far as the Tejas program is concerned. So thank you all very much for giving me the great honor of speaking to you. And I hope you enjoyed the talk.
Thank you, sir. Thank you.
Very much.
Thank you. I am leaving now. Thank you.
Thank you.
Thank you.